Hello students, welcome back. Let us resume our discussion on section 1, orthogonal basis. Previously, we went through the definition of the orthogonal basis and orthonormal basis. And then we went to an application. If we have an orthonormal basis system in place, and consequently, if we have the coordinate expressions of vectors v and w under the orthonormal basis, then the scalar multiplication, the scalar product computation can be done just like the usual dot product computation like this. x1, y1 plus x2, y2 plus x3, y3 plus all the way over to xn, yn. That was nice, and that kind of illustrated the importance of orthonormal basis. It made the computation of scalar product much easier compared with some other examples, and also it showed the clear connection between the standard dot product and the scalar product, which was a generalization of that dot product basically. However, it opens up another question as a matter of fact. If we have orthonormal basis, great, we have all that. But what if we don't have it? Does it exist? Can we construct it and go from there, or something more weird? Well, that's going to be answered in 1.5 of this notebook, Gram-Schmidt orthogonalization process. As a matter of fact, this shows you that the construction of orthogonal basis system is possible, and once you get an orthogonal basis, then you can normalize, unitize each basis vector and make them into unit vectors, and then you can get orthonormal basis, and then you can start all kind of computation from there. So this is not just a computational formula, but also it's a proof of the existence as well. So it's significant, but as all significant theorems are, we need some preparations. So let's go with a couple of preparations, and the first is an easy one. I think I left this problem as a homework problem, or at least, and I must have assigned some problem that is very similar to this as a homework. So I'm not going to go too deeply into this. It goes like this. If you have m mutually orthogonal non-zero vectors, w1 through wm, then they must be linearly independent. How do you prove that? Well, here's a sketch. You have to prove the linear independence, so set up a linear combination and set it equal to 0, and you have to prove each coefficient ai is equal to 0. How do I do that? My suggestion is to take scalar product by wi, so that's my suggestion. wi, scalar product of this, and then go from there, do some simplification, and eventually you'll have to use mutually orthogonal at some point, and your goal is to prove that each ai is equal to 0. Good luck. And then let's go over to another preparation, and this is going to be a little bit harder. Let's go to this picture, parallel and orthogonal component vectors. And here we go. If we have vector w, and from another vector v, we can find a vector perpendicular to w, like this. How do I do that? You can decompose the vector v into two components, parallel component, cw, and orthogonal component, v minus cw. So basically it's this, cw plus v minus cw. That's parallel component, and that's the orthogonal component vector. So parallel component vector is of course scalar multiplication times W, so it's easy to see. And then orthogonal component, V minus CW, V minus that. But the important thing is, what is this C? Please remember this, V dot W over W dot W. Now that was for only one vector, W. And then from this one dimension, I can add another dimension to go to second dimension. So one vector red, and then the other vector blue was not perpendicular, but we could find a perpendicular vector, this brown vector. So we went from one dimension to two dimension. Now, how do we go over to higher dimension? It's here. Okay, please take a look at this blue vector. Clearly, this is not perpendicular to this plane down here. I can't see things very well, so let me erase these green vectors here. Okay, I'm removing these greens. And then excuse me, there was a typo. Let's see. Okay, let's close this cell and then let's see how things working. Okay, all right. Okay, we have this blue vector, vector V. That still doesn't look very good. Excuse me. No, that'll have to do. I don't want to use too much class time just adjusting this program. I have to talk about mathematics here. So, okay, this blue vector is clearly not perpendicular to all those vectors down in this plane. It's tilted. But if we take the orthogonal projection vector, this red vector, which is a shadow of this blue vector, if you take light from perfectly from above, and excuse me, I take it back. Let me adjust this program just one more time. Does it look better? Yes, but I was not very lucky in my graphics. Okay, all right, that's better. So, okay, let's look at it from straight from the above. And the red vector is the shadow of that blue vector, which was tilted. And then that's called orthogonal projection. And then if you take subtraction, blue minus this red, then we get this brown vector. And this brown vector is clearly perpendicular to everything in this plane down here. So this brown vector is the perpendicular vector we are looking for. This is going from 2-dimension to 3-dimension. You see this red and blue, red and black, and you can see both are perpendicular to brown. Blue, on the other hand, clearly not perpendicular to anything. So how did you get that brown vector? We obtained it by V minus the linear combination C1W1 plus C2W2 all the way over to CNWN. Of course, the picture I showed you had only 2-dimensional. C1W1 plus C2W2, only those two. But you can generalize. It's a generalization of this. V minus CW, that was just one dimension. And here, V minus C1W1 plus C2W2 plus all the way over to CNWN. So this is the orthogonal projection vector on the plane, on the subspace, and V minus of that, okay, we finally have a vector that is perpendicular to everything. And That's what we are looking for. You see, we want to find out orthogonal basis. So we have some basis, and then first say 5 basis vectors form a subspace. All right, all good. The next vector, 6th vector, must be perpendicular to everything of the first 5. And then the 7th has to be perpendicular to everything of the first 6, and so on and so forth. So from first to all the way up to end, or if I have some head start, from 7th all the way over to 15th, kind of like that. And the key was this. No, not that. V minus the linear combination, C1W1 plus C2W2, and so on. Each Ci, of course, was the same C, V dot W over W dot W, with all those indices. Okay, I think we are ready, so let's go. Let V be a finite dimensional scalar product space, and let W1, W2, W3 all the way over to Wm are mutually orthogonal non-zero vectors. We have m such vectors, but you can start with just one. In that case, you don't have to worry about mutually orthogonal or anything. Then the exit vectors Wm plus 1, Wm plus 2 all the way over to Wn. Basically, I can add m minus m new vectors so that W1 through Wn form an orthogonal basis. So if I start from just one non-zero vector, I can add the second vector, which is orthogonal to the previous, and the third vector, which is orthogonal to first two, and the fourth vector, which is orthogonal to first three, and so on and so forth, and we can cover all the way over to dimension n. Now, if I have a head start and have W1 to Wm, then I have m plus 1, which is perpendicular to everything as before, and then Wm plus 2, which is perpendicular to all the way to W1 to Wm, and so on and so forth. Okay, let's begin. W1 through Wm are linearly independent, so we can find a basis. So up to here, that existed before, and then we could add some more, and then we can have a basis, because a basis always must exist because we have finite dimensional vector space. And then the basis, for the basis, we have to have maximal set of linear independence. So W1 through Wm, if it is already maximum, then in that case, okay, it's m-dimensional and we can walk free. If it is not maximal, then we have to add one more, and then still not maximal, add another, still not maximal, add another until you reach the dimension. And this is something we already did in module 5, so if you forgot, you can go back there. Anyway, the key thing is W1 through Wm, we have mutually orthogonal. Wm plus 1 to Wn, just linearly independent, but no orthogonality yet. Now, how do we get the next vector, Wm plus 1? We get it using the same idea, the orthogonal component vector, Vm minus 1, this one, minus the orthogonal projection of Vm plus 1. C1W1 plus C2W2 plus C3W3 all the way up to CMWM. More precisely speaking, we have all those C expressions here where V is Vm plus 1. So basically what we are trying to do is this Vm plus 1 gave us this Wm plus 1. So this Wm plus 1 will replace this one. And then we do the same thing with Vm plus 2, and then do the same thing with Vm plus 3, all the way until Vn. So we have our Wm plus 1. Okay, we have to check something for WM plus 1. One small, one big. One small, here we go. And Vm plus 1 actually belong to the span W1 through WM, yes. And then WM plus 1, because this Vm plus 1 is, as you can see, a linear combination of W1 through Wm and also Wm plus 1. All you have to do is to flip this one to the other side, then we have this linear combination. So Vm plus 1 belongs to the linear combination of this. So yes, W1 through Wm plus 1 generate Vm plus 1 as well, but that's a little fish. If you use dimension theory, then you can bypass that generating thing, so it's a little fish. Big deal is this. Is Wm perpendicular to everything up to first m? Let's check that. Wm plus 1, and let's take the dot product by arbitrary Wi, where Wi can be W1 up to Wm arbitrary. Okay, Wm plus 1 was defined like this, so taking the dot product, we just distribute Wi to each. So that, and then like this. And then please note that W1 dot Wi is 0 because of the mutual orthogonality. W2 dot Wi, that's also 0. W3 dot Wi, all 0. All the way over to Wm dot Wi, they're all 0 except this one, Wi dot product of itself. This is the only thing that survives. Everything else, actually they go down to 0. All these go down to 0. Only this one survives. Okay, alright. So Vm.wi and then this thing times Wi.wi, but then again look at the denominator. This and that cancel each other out. So what do you get in the end? Wm plus 1.wi minus the same thing, so we get 0. Conclusion. Wm plus 1 dot any Wi is equal to 0. Therefore, we have the desired mutual orthogonality to everything up to W1 through Wm. So we got a basis from W1 through Wm, and then now Wm plus 1. We got a basis. Oops. So this one up to here, all perpendicular, mutually perpendicular, and the next one. And we can do exactly the same thing with this one, using all those, using the same argument, just adjusted indices. So repeat, 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 and then what do we get? We got everything that is mutually orthogonal, and this process must stop because mutually orthogonal means linearly independent, and the maximum number of linear independent is n because we started with n-dimensional space. So that completes the proof. Not only that we proved that orthogonal bases exist, but we actually found out the computational formula, how to find it out. This formula, by the way, it's recursive and it's tedious for humans, but computers can handle in no time. That is called the Gram-Schmidt orthogonalization formula.